Okay, so we are about to get the last speaker on screen. So the last one will be about open data platform for improving traffic management. Speaker is Iisakki Kosonen from Aalto University, and well, I will activate again in a few seconds the relative poll. I will now stop sharing this so you can start sharing your presentation, and Iisakki, the floor is all yours.
Can you start the video?
Yep.
Okay. Hello, everyone. My name is Iisakki Kosonen. I'm a researcher from Aalto University, and today my topic is this Smart Junction project and open data platform for improving traffic management. So this project is part of this Jätkäsaari Mobility Lab, which Juho was talking about, and I will first go through the technical sides, and then some examples of what kind of research we are doing in the Aalto University related to this project. Okay, so just a quick thinking what is behind the idea behind here is that we have different levels of support for drivers in vehicle automation. So why don't we introduce a similar thinking in the infrastructural side, so that at the moment we are in the level 1 where we have the ordinary traffic signal control. And now in this Smart Junction project, we are working on our way to the next levels of providing real-time information and access to control or guidance to the vehicles, and finally towards the higher level of automation. So we are working in several phases. So the first phase is to install sensors to the junctions. At the moment we are installing radars and cameras, and then we will also have access to the floating car data, like public transport in the first phase, later other vehicles possibly, and then this data will be fed into a model that is modeling the traffic situation, and we compute a different measures of performance, and we also offer an open API for the raw data and also for the calculated or processed data. And then the second phase is towards optimization and control of traffic signals and other control measures, and I will speak about this later in more detail. And the third phase is related to the connected and automated environment and adding new type of sensors like air quality and emission sensors and so on. Okay, so our aim is to install 7 junctions in the Jätkäsaari. This is the main corridor out of and into the Jätkäsaari, and we will install these sensor stations that are in each junction and pointing towards each approach of the junction, and each of these sensor station have this camera and radar and the box for the communication and the processing of the data. And additionally, we can have a position access to the traffic signal controller, getting the traffic signal states and traffic detector states, and positional data, positioning data of public transport and emission data. And here is an example of the first station installed in the Jätkäsaari, and so basically we get this kind of video data nearly in real time, couple of seconds behind, and then we will install, of course, this more. And the benefit of a camera is that you can detect the objects better, and we will add some AI to detect this, what is car and what is vehicle and what is cyclist and so on. And then we have the radar input. That the benefit of radar is that it gets more accurate positioning and speed of the vehicles, and but it doesn't recognize the type so well. But it works also in different weather conditions. Here at the top of the picture, you see some of these APIs that we are working on. This WebSocket API is providing the positional data, and then vehicle trips is data like travel time is provided through this REST API. There is a startup company called Convex that is providing this technical side of this project. Okay, now let's move on to the research side, which is supported by the Henry Ford Foundation. And first, we are building a simulation model of this area, and we want to get this real data of the traffic demand that we get from these sensors. We use it for simulation different alternatives of traffic signal control strategies and optimization and different aspects, and possibly also route guidance and connected and automated simulation of connected and automated vehicles too. The other aspect is that we use the simulation model also for state estimation of the traffic situations. We call this like real-time digital twin, so that we know the speed and position of each vehicle at any time in real time. And the simulation model is used for sensor fusion, noise reduction, filling the gaps between the sensors, getting a detailed traffic situation model, and getting new type of indicators for the traffic signal control. Here is one example of research on traffic management and optimization of traffic signals. This is related to more connected car environment, because here the idea is to use, instead of the vehicle throughput, is to optimize the throughput of the road users, and this requires information about how many passengers there are in a vehicle. And so here the process is to first predict the throughput of users through the intersections, and then optimize this throughput, and then finally adapt the traffic signal control to maximize the user throughput. One intersection simulation model is used here, and different combinations of vehicles. Here, some of the vehicles have 1 passengers, others have 2, 3, or 4 passengers within the car, and there's low traffic and high traffic conditions simulated. The signal control options here are user-based signal timing, vehicle-based signal timing, and vehicle-actuated, traditional vehicle-actuated control. And the results show that both user-based optimization and vehicle-based optimization. They improve the user throughput compared to the vehicle-actuated control, and the user-based optimization also performs slightly better than the vehicle-based optimization. And of course, the performance also depends on what is the rate of the connected vehicles available. So the more of connected vehicle and more of this data of passengers in the car you have, the better you can optimize, and the performance is better in terms of delay or user throughput. But you can see from these pictures that already from some penetration rate of 40%, you can start getting better results than the vehicle actuated control. And then another aspect of research is this policy-based optimization. The present challenge is that the controllers in the field, they don't really accept the policy as an input, but instead there is a big number of parameters, and it is difficult to understand the effect of this and what is the effect on the policy. And what we aim here is to provide a simple access to the policy input, reducing the number of parameters, provide tools for policy optimization, and finally automatization also for the optimization according to the policy input. So alternative policies may include minimizing the emissions, which is getting more and more important in the cities, favoring certain vehicle type like public transport or trucks or bicycles or pedestrians, favoring some certain route or so on, and also the trade-off in optimization delays versus the stops, which can be sometimes a bit contradicting. So here we have a policy tuning framework for working on this, and the first loop here is the traffic simulation versus traffic signal controller loop, which is controlling the traffic in a simulation or in a real situation. And the second loop is this optimization loop that get these policy indicators from the traffic simulations and then evaluates the fitness of them and then provides new parameter sets for the signal controller. And the third loop is this policy tuning loop that gets the performance results and then provides policy definitions to this optimization loop. And here is an example. This is a big intersection in San Jose that was simulated, and in step one we made a single criteria optimization that we can see what are the boundaries that can be achieved by optimizing with one criteria only. So we will see that the first policy is the level of service, and you get to the certain minimum. We tested the green bar here, and if the second picture is the environmental policy, and you get the minimum amount of stops, which is also the green bar here. And these values then provide us a boundary box for the policy tuning that then the user can adjust these what values are tolerated as a level of service and as a percentage of stoppage vehicles, and then you can try different policies and what are the performance of those. And yeah, then a third avenue here is this kind of what we could call smart priorities or something like that. And the traditional priorities for traffic signals, they are for public transport only, and they are usually given always when requested, and assuming that there is a big vehicle with a lot of passengers. The smart priorities, we think that they depend on multiple factors, like what is the overall situation and the density of the traffic, what is the impact of the priority cost to the other traffic if the vehicle is being late, and what is the number of passengers if that data is available, and also extending the idea towards that we can give these priorities not only to public transport, but for example, moving platoons, like what is the case that we have in Jätkäsaari, that there is very dense platoons coming from the harbors when the ship is coming to the harbor and discharging the trucks straight towards the street environment. So this is more preliminary. I don't yet have the exact numbers for you, but the preliminary results are encouraging. So we hope this could also provide some help in this Jätkäsaari project. And finally, we are heading towards so-called cooperative traffic management. We are now focusing on traffic signal control optimization, but then we have also two alternative routes out of the Jätkäsaari. The other alternative routes is only for passenger cars, so they can be guided to this route, depending on the situation in the main route. And then we can get information of ferry arrivals, the arrival time, and the expected vehicle count out of the ferry. And this system can give a heads up to the traffic signal control system and the route guidance, how to optimize their systems and prepare for the heavy traffic that is coming soon. And yeah, so although now we are focusing on stationary sensors like the radars and cameras, but we are heading towards the more connected environment and also keeping in mind automated vehicles. So we can use that connected information for improving this traffic state estimation, providing wireless traffic signals, speed and lane advisory for the vehicles, platoon forming, getting the passenger counts from the cars, and different type of safety alerts for the road users. Okay, so that's all. If you want more information, you can contact me or other persons of our smart mobility team in Aalto. And if you have more technical questions regarding the APIs or so, you can contact Kari at ConvexFi about accessing the data. Okay.
Okay, thank you very much, Iisakki. Well, one quick question again from my side. Do you think there is an exact amount of data that we need to know, or the more the better?
Well, Yeah, I generally speaking, I think the more the better, and then we will learn is there a certain amount that is already sufficient. But at the moment, I would say the more the better. Then we can do research and see what is if at some cases we actually can manage with less data. And the more is also good because we can then validate the data against other type of sensors. So yeah.
Okay, thank you very much.